Hello and welcome to Chapter 6, Computational Exercises. So rather than picking a textbook example, let's create our own simulation. Let's say we have two projects to pick from. One of them is a 6-year lived project with these cash flows, and the other one, project B, is a 2-year lived project with these cash flows. Initial investment of 100 and then positive cash flows of 200 and 300. Which one should we pick if we are to use the net present value method or the net future value? So in those cases that we are told to use the net present value or the net future value, we have to transform these projects into two equally lived ones by finding the minimum common multiplier between these two projects. So for project A, we are looking at a multiplication table for 6, the maturity. And for project B, we are looking at a 2-year lived project, so the multiplication table for 2. Since this is the lowest number, we start on this one. So from elementary school, you know that 2 times 1, 2, 2 times 2, 4, 2 times 3, 6. And you know that 6 times 1 is 6. So this is the minimum common multiplier, which means we have to create 3 replicas for project 2 in order to turn this one into a 6-year lived project. So to do that, to start the first replica, recall that the last year of the first replica is year 0 of the next replica. So to start another replica, we need to invest 100, and then a year later we get 200 positive cash flow, and then 300 again. However, we need to create a third replica. So the third replica starts at year 4. So we need to invest again 100 to get 200 and then 300. So now we have two equally lived projects where the net cash flows here, this cash flow, we can simply write 200, and here also 200. Now we can compute the net present value for each one of them to evaluate which one should we choose. To do so, we need to have a minimum acceptable rate of return given to us. Let's say it's 10%. So the net present value for project A, it's equal to negative 200 plus 100 discounted 1 year at 10% plus 200 discounted 2 years at 10% plus 500 discounted 2 years at 10%, then the 300 discounted 4 years, and then the 200 at year 5 discounted 5 years, and then the 400 at year 6 discounted 6 years at 10%. And this would give 986.73. So the net present value for project A is 986.73. Then you will do the same rationale for project B. So for project B, negative 100 but times 0, no need for adjustment. Then 200 discounted 1 year at 10%, then 200 discounted 2 years at 10%, then 200 discounted 3 years, then 200 discounted 4 years, then 200 discounted 5 years, and then 200, and then 300 discounted 6 years, and these would give 827.50. So which one is the best project? Project A gives a higher net present value if we are to use the net present value as the selective tool. Now let's say you were told to use the net future value. Net future value for A would be the negative 200 pushed forward 6 years, future value, right? Then the 100 pushed forward 5 years, then the 200 pushed forward 40 years, then the 500 pushed forward 3 years, then the 300 pushed forward 2 years, then the 200 pushed forward 1 year at 10%, and finally the 400. And this for project A would give you $1,748.06. So the net future value for A is 1748.06. Then you'll have to compute for B. You can pause the video if you want to see the computations with more time. So the net future value for project B would be negative 100 pushed forward 6 years, then 200 pushed forward 5 years, then the following 200 pushed forward 40 years, then the following 200 pushed forward 3 years, and then the following 200 pushed forward 2 years, and then the 200 at year 5 pushed forward 1 year, and then the 300. And these would give you 1465.97. So which one is the best project? Again, project A, because it has the highest net future value. Now we have project A with 1748, we got project B with 1465.97, and then let's say we want to find the annual worth. And the annual worth, in this case, let's use the future value of an annuity. So the annual worth for A, future value of an annuity formula, so this will give for A 1748.06 equal to A, then 1 plus the 10% interest rate to the power of 6 minus 1 divided by 0.1. And for annuity you would get 226.56. So annual worth for project A, 226.56. Then you would repeat these for project B, so 1465.97. What is the annuity given that future value, given that the interest rate is 10%, 6 years, and interest rate is 10%, so this would give you an annuity of 190.00. So again, showing us that the best project is project A. So the annual worth for project B is 190. For project B, now note that if you were to compute the annual worth for the original cash flow series, and remember the original cash flow series was this, the project, you will also get an annual worth equal to 190. What I'm telling you is, if you are to compute the future value of this, so the future value of an annuity formula, and I'm going to put all the future value in one bracket, so that will be the negative 100 pushed forward 2 years, 1, 2, right? Plus the 200 pushed forward 1 year at 10%, 1 year, plus the 300, that's the future value, right, of this project B. What is the annuity given the 10%, 6 years, the annuity formula, right, given the future value? You will find this to be 190. So as is shown in the textbook, the annual worth is the most robust method among the absolute value methods. That is, compared to the net present value and compared to the net future value, annual worth is more robust in the sense that it will surely give you the right answer without the need for adjustments based on the original cash flows. You only need to do the transformation if you are using the net present value or the net future value. Now let's compare these projects using the relative value methods, the methods based on the return per dollar invested. Before we proceed, let's recall that the absolute dollar methods, they all indicated that project A was the best. Highest net present value, highest net future value, highest annuity. Let's see if the relative value methods say the same thing. Let's start with the internal rate of return. So the internal rate of return is the rate that makes the net present value equal to 0. So 0, actually let's start with project B. Negative 100 plus 200 discounted at the internal rate of return, the interest rate that we are trying to find, 1 year, pushed back 1 year, and then the 300 pushed back 2 years. And using the solver or interpolation, you would find that the internal rate of return is equal to 2. The same is to say 200%. And note that if I was to compute the internal rate of return for the same cash flow series with the equally lived projects, remember what we had was 200 every year up to the last where we had 300. If you were to compute the internal rate of return for that, it would look like an extended version of this one, where we have the 200 series. Could also use the annuity formula if you wish, but let's just keep this as simple as possible, plus the 200 discounted 5 years, plus the 300 discounted 6 years, you'll get the same 200%. The return per dollar invested does not change. So the relative value methods are more robust than the absolute value methods in evaluating the best project. So we found out that the internal rate of return for project B was 200%. Now let's look at the internal rate of return for project A. So for project A, let's make it a different color, it would be 0 equal to negative 200, and you'll get that the interest rate would be 0.9745, the same is to say 97.45%. So based in the internal rate of return method, they are both acceptable projects because the internal rate of return in both is greater than the minimum acceptable rate of return. And now the project B stands out as the best one because it's 200% internal rate of return, whereas for project A is only 97.45. So it's contradicting the recommendation of the absolute value methods. It's saying that project B is better now if you use the return per dollar invested. let's look at the other two tools, actually the new tools introduced in this chapter. So the benefit cost ratio, which is also a relative value method. So the benefit cost ratio is the ratio between the present value of the benefits divided by the present value of the costs, both evaluated at the minimum acceptable rate of return. So for project A, this will be the benefits is the positive cash flows. So 100 discounted 1 year at 10%, 200 discounted 2 years at 10%. It's basically the net present value without the negative cash flows. So 500 discounted 3 years, then the 300 discounted 4 years, then the 200 discounted 5 years, and then the 400 discounted 6 years. That's all in the numerator, and in the bottom the present value of the costs. Do not put the negative sign, because by definition whatever is in the denominator is already a cost, so it does not come with a negative sign. The BC ratio is greater than 0, always, does not assume negative values. But a BC ratio is only worth it if it's equal or greater than 1, because it means that the benefits outweigh the costs. If the BC ratio is less than 1, then it's not worth it the project to even consider further, because it's giving us a loss. The benefits are smaller than the costs if the BC ratio is smaller than 1. If what is in the numerator is smaller than what it is in the denominator. So to be acceptable, this ratio has to have greater or equal to 1. And in this case, you will get the ratio of 1186.73 over 200, which means a BC ratio of 5.9337. Greater than 1, so acceptable. This is the BC ratio for project A. So let's put it here. BC for A equal to 5.9337. And we'll have to do this for project B, and let's use that. So for project B will be 200 discounted 1 year, 200 2 years, 200 5 years, plus 300 6 years, divided by the present value of the cost is 100, because the cost is only happening at time 0. So this would give you 1365.97 divided by 113.6597. Again, indicating that project B is better. It has a higher BC ratio than A. Now, the tools that we learn as relative value method, they all have to give the same recommendation as which one is the best project. And so far so good. The internal rate of return and the BC ratio are indicating project B to be the best. When we looked at the absolute value methods, the dollar-based methods, then they all indicated A to be the best. Net present value, net future value, and annual worth was greater for A. So that was consistent. Within families, they have to be consistent. For example, if the net present value would say project A is best, but net future value would say project B is best, then we did something wrong. Within families, they have to be consistent. So all absolute value methods have to point to the same project, and all relative value methods have to point to the same project. Now, the absolute value method does not need to give the same recommendation as the relative value method, because they are looking at different things. The absolute value methods are looking at the amount of dollars that you're going to earn, whereas the relative value methods are looking at the percentage return per dollar invested. That's why they are a better method. So to conclude the relative value methods, we still have to do the other new tool that we learned in this chapter, which is the external rate of return. To compute the external rate of return, you need to be given a reinvestment rate. If you are not given a reinvestment rate, then you use the minimum acceptable rate of return as the reinvestment rate. But let's say that I'm giving you, and that's what I typically do in the exercises, for example, in quizzes. So let's say that there is a reinvestment rate of 8%, meaning that you are going to reinvest the positive cash flows that you earned throughout this project in some financial security that gives you an 8% return. This is different than the overall return of the projects, right? The minimum that you want in those projects is 10%. This is a rate at which you are reinvesting the positive cash flows that you get throughout the project. Because why not make money with those positive cash flows? This is the key difference relatively to the internal rate of return. The internal rate of return ignores that these positive cash flows can be reinvested. They pretty much assuming that you're putting them under the mattress. That's not really realistic. Right? A savvy investor keeps on investing their money as the positive cash flows come in. So that's what the external rate of return does. So the external rate of return, the concept is the future value of all costs evaluated at the external rate of return must equate the future value of all benefits evaluated at the so-called reinvestment rate. What it means is that we're going to compute the future value of these, for example, for project B, of these cash flows, allowing them to earn 8%. So we're going to get a number here. And on this side, we have the computations of future value of the costs at an unknown rate. So we're basically looking what is the break-even rate, right? Because we are equating costs to benefits. So if the costs are equal to benefits, when you add them up is equal to 0. So it's a break-even rate, but now focus on the future value and allowing the cash flows to be reinvested. Similar for A, right? This is going to be the benefits, the positive cash flows, and that's the cost. So let's start with A, following this rationale to find the external rate of return. So we're saying, okay, again, no need to put a negative sign because by definition, whatever is on the left-hand side of the equation is a cost. So pushing forward the 200 to times 6 at the so-called external rate of return. So we're going to push it forward 6 years. What is the rate that makes this value equal to the future value of these cash flows when they are reinvested at 8%? So let's push forward the 100 at 8%, 5 years. 1, 2, 3, 4, 5. Then push forward the 200 at 8%, 40 years. Then push forward the 500 at 8%, 3 years. Then push forward the 300 at 8%, 2 years. Then push forward the 200 at 8%, 1 year. And then the 400. So you would get 200, 1 plus the external rate of return to the power of 6 equal to $2,014.81. Then you solve for the unknown, the external rate of return, and you would get 0.4696. The same is to say 46.96%. That's the external rate of return for project A. and it's worth comparing it to project B because it's greater than the minimum acceptable rate of return, or the minimum external rate of return if it was given to you. You can also have in the exercise a minimum external rate of return, and that's the one you compare to this one. So the project has to give external rate of return greater than the minimum external rate of return required. Or if you are not explicitly given a minimum external rate of return, you compare it to the minimum acceptable rate of return. So in this case, that's all we have, so we're going to compare with that. And it's greater, so it's worth further consideration, which means let's compare with project B. So we got an external rate of return for project A of 46.96%. And now, to be consistent with the other relative value methods, this project B external rate of return has to be greater than 46.96. Let's find that out. So the cost is 100 pushed forward at the external rate of return during 6 years, and then the future value of the positive cash flows reinvested at 8%. So the first 200 pushed forward 5 years, then the second 200 pushed forward 40 years, and so on. 3 years for this one, then the next one pushed forward 2 years, then the next one pushed forward 1 year, and then 300. And this would then give you 100 1 plus the external rate of return to the power of 6 equal to all these. The future value is 1567.19. So then you solve for the external rate of return and you would get 0.5819. The same is to say 58.19%. So better than the minimum acceptable rate of return and better than A. So project B, all three tools, the internal rate of return, the BC ratio, and now the external rate of return, point for project B as the best, whereas the dollar-based return methods pointed for the A. The conclusion is, overall, most sophisticated businesses use the relative value methods. So the most knowledgeable businesses would focus on select project B. However, less sophisticated businesses tend to focus on the dollar amount that the project gives instead of the percentage return. And that is the net present value, net future value, and the annual worth. So those businesses would select project A instead of project B. So this exercise pretty much shows you everything about chapter 6. Not all exercises need to be this complex, but you learn how to use the absolute value methods when facing differently lived projects and transform them into equally lived projects. And you learn how to use the BC ratio, the new tool, and the external rate of return. The last topic worth mentioning is the payback ratio. If you were to have a tie between these projects, which one would we pick? Imagine that both projects would give 46.96. We would break that tie using the payback period method, the naive method as highlighted in the textbook. So the issue is, ignoring the time value of money, how long would it take you to recover your initial investment? So look, for example, for project A, we invest 200, right? Let's put here how much we are left to recover. So at time 0, we invested 200, right? A year later, we get a positive cash flow of 100, which means we now just have 100 to recover. And then the second year we would recover 200, but we don't need all that to break even. We just need half of it, right? We only need 100, but we are getting 200 this year, so it means we only half a year, 0.5 of these 50% of this year. So the payback period for project A is 1.5 years. That's the payback period, 1.5 years for project A. For project B, how much would be this payback period? Well, we invest 100, and at the end of this year we're going to collect 200. So we only need 100 of these 200 to break even, which means 0.5 years. So the payback period for B is merely half a year, 0.5 years. So if there was a tie, we still would pick project B because it has a shorter payback period. You recover your money faster. But again, you are never to use the payback period to select the best project alone. You can only use the payback period if you already used one of the other methods. The payback period by itself shall never be used to select the best project. Payback period method is only used to break up ties. Remember, it's called the naive method, right? So never use it by itself to select the best project, only to break up ties. This is it about chapter 6.